Dear Professor and faculty member, my name is Sukma.meganova Effendi. I'm a doctoral student in Tajamangala University of Technology, Tanyaburi. In this video, I want to explain about tooling planar robot in forward kinematic. This is the outcome of this project. This is a MATLAB program that generates forward kinematic of a tooling planar robot under two conditions of rotational movement value or joint angles with variable q, with length of the first link or arm L1 in a blue line is 8, and the second link or arm is L2 in red line is 9. This picture shows the result of the forward kinematic with two conditions of joint angle. The first joint angle is 5 divided by 4 and 5 divided by 3, and the result is like this. And then in the right picture, this is the forward kinematics of tooling planar robot with the joint angles -1 and 2. Before we know the experimental of this project, we have to know about the principle of tooling planar robot. There are pictures in here. This is the illustration of tooling planar robot. This is a type of arm robot that has two movable joints. So this robot also has two degrees of freedom to move its two arms. This is the first joint, this is the second joint, and this is the symbol for the first degree of freedom, theta, and then this is the second degree of freedom, this is pi. And this is the end effector with the coordinate x, y. The movement of a robot is determined based on kinematic equation for any given degree of freedom robotic arm. There are two kinematic calculations, forward kinematics and inverse kinematics. The forward kinematics is used to determine the position and orientation of the end effector, given the value for the joint variables of the robot. Given joint variables with theta pi, theta pi to obtain xy coordinate. And then the inverse kinematic is used to determine the joint variables of the robot, given the value for the position and orientation of the end effector. Given the value of the position and orientation of end effector xy to obtain joint variables theta pi. Okay, we can see in this picture to find the coordinate of position and orientation of the end effector xy in here. We have to know the picture first, the analysis of this picture. This is the first joint with the coordinate x0, y0, and then this is the second joint with the coordinate x1, y1, and this is the end effector with the coordinate x2, y2 is equal with x xy. So in this first arm, in this first link, there is a degree of freedom. The name is theta. This is the degree of freedom based on the 0 in x-axis toward the end movement of link 1. And then in here for the second link, also there is a degree of freedom. The name is pi. This is the degree of freedom towards the first link, towards the first link. So this is the axis used from the first link x1, and then the y-axis, this is used from the orientation from first link. And then for the n effector, the x-axis is towards the second link, and then this is the y2 axis. And then for making the calculation of forward kinematics, because in this two-link planar robot, in this project, let's calculate the forward kinematics of two-link planar robot. The principle, we use the trigonometric function, like in this picture, there is a triangle, there is a theta, and then if I want to calculate sin theta, we have to use or equal to O divided by 8. Sin theta is equal to O divided by 8. And then cos theta is equal to A divided by 8. And then tan theta is equal to 0 divided by A. And then we can determine the coordinate of x1, y1 by using the principle of trigonometry. This is the coordinate x1, y1. This is the triangle of determine the x1 and y1. So from the angle, from the theta, we can calculate x1 and y1 by, this is the length of x and this is the length of y1. So we can calculate for x1. So x1 is like this. So we use cos theta. And for y1 is like this. The calculation will use sin theta. So the x1 is equal to L1 multiply with cos theta. And then y1 is equal to L1 multiply with sin theta. From the basic principle that used to determine the coordinate join 2, x1, y1, and n factor x2, y2 with trigonometric function that shown like in this picture, like the previous slide. Then the coordinate x, y, y1 and x2, y2 can be calculated using this equation. This is like from the previous slide for determine the coordinate join 2, and then for the coordinate n factor xy that equal with x2, y2. We can see in this picture the angle for or the degree of freedom of this link is same with theta plus with pi. This is the total angle or degree of freedom the second link. And the principle is same, use the trigonometric with the angle is theta plus p, and because the n factor is equal to first link plus second link. And then we can see in here the coordinate x is equal x2 is equal to L1 multiply cos theta plus L2 multiply with cos theta plus pi. And then the y coordinate is equal to y2 is equal to L1 multiply with sin theta plus L2 multiply with sin theta plus pi. So this is the total of x1 plus x2 and y1 plus y2. Theta is the joint angle, where the theta is joint angle from joint 1 to joint 2. Pi, this is joint angle from joint 2 to the n factor. L1 is the length of arm or link from joint 1 to joint 2. And then L2 is length of arm or link from joint 2 to the n factor. The forward kinematics calculates the position of the n factor. The equation is like this, like the previous slide. The x coordinate, this is representing the total x distance traveled by the n factor. The first term gives the horizontal projection of the first link, and the second terms adds the projection of the second link. So the y coordinate, this is representing the total y distance combining the vertical projection of both links. In the MATLAB, the matrix join coordinate variable q and Cartesian the n effector with coordinate variable with variable p as shown below. This is the matrix of Q. This is column matrix with the element of theta and pi, and this is the P matrix. This is also column matrix with the element x and y. And the MATLAB function that used to calculate the forward kinematic is just like this. This is the function calling the variable q. This is the example of calculation of forward kinematics to link planar robot. The first example is use the joint angles for variable q with the element pi divided by 4, and the second element is pi divided by 3. This is like a row matrix. So we can calculate the value of pi divided by 4 and pi divided by 3. Pi is equal with 180. So the pi divided by 4 is same with 180 divided by 4, and then for the pi divided by 3 is equal to 180 divided by 3 is equal to 45 degrees and 60 degrees. Then for calculating in the forward kinematic function in the MATLAB, we have to convert it the degree value to the radian value. We have to know how to convert the radian to the radian. 1 degree is same with 22 divided by 7 and then divided by 180. This is for convert from degree to the radian. So from this, only multiple to the degree value. So for the first element, for pi divided by 4 is same or equal to 45 degree multiple with 22 divided by 7 and then divided by 180, 180, and then for the second element, pi divided by 3 is equal to 60 degree multiple with 22 divided by 7 and then divided by 180. So the result for the first element in the radian value, this is 0.7857, and then for the second element from pi divided by 3 in radian is equal to 1.0476. Then after that, we can validate in the MATLAB. We write the M file first, and then after the M file of the forward kinematics is done, we can put the variable value of key. This is pi row matrix with element pi divided by 4 and pi divided by 3. The result is similar, and then after that just call the M file name for forward kinematics with variable q. So the answer of the first example of joint angle for forward kinematics tooling planar robot is the x is 3.3275 and then the y is 14.3502, and the illustration is like in this picture. This is the join 1, join 2. This is the first link, L1. This is the second link, L2. For the joint angle of first link is 45 degree. In radian is 0.7857. And then for the second link, the joint angle is 60 degree. The orientation is from first link. Because this is a positive value of joint angle, the movement is go to the or turn to the counterclockwise. If the value of joint degree is negative, then the robot will move clockwise. And then this is the result. This is the value of coordinate xy or coordinate of n effector. This is 3.3275 and 14.3502. And then this is for the second example. The way to calculate is same like the first example. Calculate the value of Q in degree and then this is convert to radian, and then the value is like this. For value of the first element of key is -1 is same in radian minus 57.2728, and then the value of 2 is same with 114.5455. I'm sorry, this is not used in here. Just use the value of matrix with the element -1 and 2, and this is not used in here, not used in the second example. And then in the MATLAB, the same. After the M file is done to make, then just put or give the value of matrix Q. This is the joint angle with the element -1, and then the second is 2. Then call the M file name of forward kinematics tooling planar robot with the variable Q. So the answer of the position and orientation of an effector coordinate xy is the x 9.1851, and then y is 0.8415, and then the illustration is in like in this picture. This is the first joint, this is the second joint, this is the first link L1, and this is the second link L2, and this is the coordinate of n effector. From the first joint angle, the value is -1 is same with minus 57.2728 degree. So The movement is go to the clockwise. I'm sorry, the angle is. And then the second joint angle from the orientation of L1 from the first link. The value is 114.5455 degree. This is go to move to the counterclockwise, different with the first joint angle. And then the result of the coordinate xy coordinate of n vector is 9.1851 and 0.8415. Then I will show the simulation in the MATLAB. This is the M file of the forward kinematic of two-link planar robot. This is the function for forward kinematic. This is for calculate the position of the n vector of the robot in 2D space using the joint angle of Q and the length of L1 and L2. And this is the initialized declaration of the value of L1 and L2. L1 is equal to 8 and L2 is equal to 9. This is first link and this is the second link. And then declaration of the theta and pi. This is read from the matrix of Q. This theta is for the first element of Q, the joint angle of the first link. And this is given from the user input. And then for the pi is equal with matrix, element matrix of Q for the second element. This is also given from the user input. And then this is the equation of the forward kinematics to find the position of the n vector. This is just like in the explanation of my slide. And then this is for the result in the variable p is equal to matrix with the element x and y. This is the result of 2D n vector position in Cartesian coordinates. And then this is for the plot the robot configuration. Just put write the figure. This is for obtain a new figure window. And then this is the function for plot a graph, plot some graph. The first, this is for plot the first link of robot from the origin 0, 0 and extend to the first link. Is shown in here. This is only the calculation of first link, and then this is for plot the second link of robot from the end of the first link and extend to the end effector. This is from 0, 0, and then go to the coordinate of x1 and y1, and then this is from the coordinate of first link, go to the coordinate value of an effector. And this is just for the labeling the axis, and this is for the limitation of x and y axis. Then after that, save the M file with a specific name, and after that, give write the value of q. This is display in radian, and then call the M file name. The name is like this. With the variable q. And then this is the result. This is for the movement from first link, and this is the movement of second link. This is 0, 0. This is the value of x1, y1, and this is the value of an effector x, y, or x2, y2. The value is same in the command window. The value of x is 3.3275, and then the y value is 14.3502. And then I will show for the second value of joint angle. -1, 2. Then call the M file with the new value of q -1 and 2. Then the result is like this. This is for the x, this is for the y value of an effector coordinate. This is from 0, 0. This is the value of coordinate x1, y1, and this is the value of an effector coordinate. This is same in the command window. X is equal to 9.18514, and for the y value is equal to 0.841471. Hey, this is all of my explanation. Thank you for watching.